We have a very short lecture today, so let's keep moving so we can finish things about the early part, at least, of the regression lectures. So what I need to do is I'm going to be jumping on the slides, going to whatever I think is most substantive. So what I want to do is I want to review the concept of the evidence approximation. We have seen it extensively, but in the context of the particular regression model that we used in the last two lectures. So what you see there is basically the predictive distribution. Some of the variables are not shown explicitly, just to make things compact. So the little t, the unbolded t, is the prediction at a new unbold x that is not shown, and this bold t are the training data, the responses to some bold x's, okay? So remember, the predictive distribution is the likelihood if you knew W times the posterior given the training data. And now you notice here, I used to have two hyperparameters in the prior model. Remind me, where was alpha coming from? Where was alpha in our models? The prior of what? The prior for W, and where beta was coming? It was the noise in the likelihood. You can actually see it there, okay? That's why there's only beta in the likelihood. So what we have here is, we also, you know, if we're gonna have a full predictive distribution, we're gonna make alpha and beta to be random variables. So really, you're gonna need to integrate out the posterior of alpha and beta given the training data, and the integration so is gonna be in the regression coefficients in alpha and beta. We already have said that this is a very sort of complicated thing to do, not just in this problem, but in many settings. So what we will do is we will use the evidence approximation or empirical Bayes. So what we will try to do is we will try to fix the parameters alpha and beta at some point estimates that I denote here with alpha hat and beta hat. So when we do regression and predictions, this distribution here is going to be really a delta function centered at alpha hat and beta hat. So effectively you get back to our standard likelihood times posterior integrating W out, but this alpha and beta are not going to be set a priori, they're going to be set using the evidence approximation of the data, okay? That's the whole idea. So we're going to discuss today how in the context of regression models we compute this alpha hat and beta hat, and also to see if there is sort of any intuition out of the results that are coming out of this analysis. The algebra actually is straightforward, so I'm going to try to go a little bit faster. We have seen this type of problems before. So this is the posterior, and we said we're going to approximate the posterior with some delta function. The posterior is written as the likelihood, and you notice here, this is, there's no W here, so W is integrated out, right? So this is the likelihood given alpha and beta times some prior, and this prior, I'm going to make it a uniform prior on alpha and beta because I don't know anything else. So effectively, if you want to find the map estimate of this posterior, it's the same as maximizing the marginal likelihood, right? That's the evidence approximation. So what is the marginal likelihood? Is basically what you see here. Is the likelihood if you knew W times the prior with W integrated out, all right? So effectively, you know what this is really the denominator in the Bayes rule when you compute the posterior for W, right? That's what we have discussed in many lectures. Again, this is the marginal likelihood written like that, okay? And we're going to try to compute a point estimates alpha and beta by maximizing this evidence. So let's see at the different terms. I don't know if you can see the notation. Maybe this is better for me. You remember this is a Gaussian, and on the exponent we had that square exponential that has the square, the mean square error, ED, that tells us how well the regression function approximates the target values, okay? And this is the prior, that's a Gaussian with precision alpha. So you can guess, right? This is a Gaussian, this is a Gaussian. This should not be a difficult thing to do. The difficult thing may be at the end of the day to do optimization with respect to alpha and beta. But before we do the optimization, we need to compute this integral. So let's simplify a few things. So if you plug in, if you have an exponential here and you have another exponential from this Gaussian, you can combine them together to another energy functional that is basically beta over 2. This comes from the likelihood. That's how well it matches the training data. Plus this comes from the prior. We agree? Right? There was an alpha of precision in the prior. There was a beta, the noise level in the likelihood. So we get an energy, the exponential that looks like that. So the first term comes from the normalization factor in the likelihood. We have n data, that's why it's the power n over 2. The second comes from the normalization in the prior. We have m coefficients, so it is this to m over 2. Okay, so that's the energy, right? So this is what we really want to compute first. And so what I'm doing is, I'm going to approximate, actually no approximation, this is exact, right? I'm going to write this energy functional in this form, where this is the value of the energy functional at the map estimate of the parameters that we have seen before. It has this form, where alpha is given by this. Can somebody look at this and tell me why it's equal to that? Or what it reminds you? All right, so I am claiming this is equal to that. So look at it, just, you know, visually, what does it tell you? What does it look like? Huh? So when I'm approximating this around the map estimate, right? This is the map estimate. This is a function of W, and I'm approximating this around the map estimate. And I see a constant term plus a quadratic term. I don't see a first order term. And so what is that? It looks like a Laplace approximation, but really here it's exact, you know, because this is a quadratic function in W. So I'm not really missing anything. Okay? So in general terms, you could have thought of this as a Laplace approximation, but you know, this is exact because this is quadratic in W. So the first term is missing because, you know, the derivative, we minimize this with respect to W, so the derivative, the first derivative is 0 to get this estimate Mn. All right, there is a reason we wrote it like this, because now this is constant, so I can move this term out. But just look at these equations, you know, so I have defined A to be alpha I plus beta phi transpose P. Phi is my design matrix, okay? And this matrix A, you know, we've seen from the Laplace approximation, it's really the Hessian, the second derivative of the energy function. Okay, so when you plug in this into the exponential, this will come outside, and this second term is trivial because, you know what? The thing inside parentheses is the exponential of from a Gaussian. So when you integrate W out, what you get is the normalization term of a Gaussian, and there is the normalization term of a Gaussian. Right? There's no calculation involved because that integral is like normalizing a Gaussian, so you will get the normalization term of a Gaussian, where this A is the determinant of the precision A that we see there. Okay? So plug in all the terms in the marginal likelihood, so what you will get is this times that, times this term, times this term, and if we make it a little bit simpler, we get the log marginal likelihood that has this nice form. So task 1 is done. We basically have a very nice expression of the marginal likelihood. I gave you lots of ways in earlier lectures on how to compute this for many different problems, all right? So if you actually look at these equations, they may look very familiar because what we derived in other examples looks similar, okay? The only complication that I see here is really having the log of a determinant here, so you may be discouraged now because this matrix A, I remind you, the matrix A depends on alpha and beta, so you have the determinant of that matrix and you're going to have to take derivatives with respect to alpha and beta. So there you may say, oops, you know, I don't know how to do these things, but the answer is yes, you know how to do these things. All right, so, oh, what happened? What did I do? Okay. So let's figure out on how we're going to take derivatives and do optimization with respect to alpha and beta. So the first thing you need to do is you need to define the eigenvalues and eigenvectors of the matrix beta phi transpose phi, okay? And I call those lambda I and ui. So you really have to solve an eigenvalue problem to do the analysis that we will see shortly. The reason we keep beta there is it will simplify the calculations, but actually in one of the slides that I may not cover in the lecture, I try sort of to generalize the analysis and I give you in one slide some insights without the beta there, okay? I mean, I remind you that there is a difference from the other slides, but keep in mind here there is a beta. All right. So what we need to do is we need to calculate the determinant of A. And so let's start taking derivatives with respect to alpha. So the first term is very easy. 1 over alpha, so there is no alpha there. E of mn, let me see, E of mn, do we have an alpha on EMN? Yeah, that's very easy, right? That's this term there, so no problem. And then we have derivatives of the log of this matrix A, and I remind you A is alpha plus beta theta transpose phi. So the eigenvalues of A, they're alpha plus lambda I. Can you see that? If the eigenvalues of this matrix are lambda I, the eigenvalues of alpha I plus beta, this matrix is alpha plus lambda I. So if you know the eigenvalues of a matrix, and you can think representation of the matrix in the eigenvector basis, right? What you will get is, you will get basically the eigenvalues in the diagonal, so the determinant is really the product over I of the lambda I plus alpha. So we need to take derivatives with respect to alpha. So this log of the product becomes summation of the logs. So we have summation. The derivative of this is 1 over lambda I plus alpha. Derivative with respect to alpha, which is 1. Done. Very easy. So we got derivatives with respect to alpha, and we are done. So if you plug in everything that I told you on the marginal likelihood, the derivatives with respect to alpha, at the end of the day, with 0 extra steps, just the rearranging of the terms, you're going to get an equation that looks like the equation you see on the bottom. So let me just read this equation. It says alpha equal to gamma, where gamma has been defined to be the summation over the eigenvalues of lambda I divided by lambda I plus alpha, divided by Mn transpose Mn. And remember, Mn is the map estimate of W. So this equation looks like a straightforward equation to find this optimal alpha where the marginal likelihood is maximized. Unfortunately, you notice that gamma contains alpha. All right, so there is an alpha inside the summation, so it's not like you can rearrange terms and put alpha on one side and say there is alpha. So the only way you can solve this equation is iteratively. And iteratively means you start with some alpha, you compute gamma, you plug it in there, you recompute alpha, and for that alpha you recompute gamma, you compute this term, you come back, hoping for the best. Okay? Hoping for the best because these fixed point iterations There is no guarantee that it will work in all cases, right? But in this particular case, it does work, okay? So I'm not going to go through the iteration. So the next thing we need to discuss, similarly to alpha, is derivatives with respect to beta. And there's only one trick here. That, so if we look at the derivative, so the log of the determinant is the log of the product of these lambda i's plus alpha, which is really summation of the logs of lambda I plus alpha. So to be able to do this, we need to know the derivatives of lambda I with respect to beta. That sounds also very complicated, the derivatives of lambda I with respect to beta. But actually, you know what? If you look at this equation, as beta increases, I mean, if you double the beta, lambda I doubles. So the derivative of lambda I with respect to beta is nothing else but lambda I over beta. Okay? And that's exactly what I have here. You notice here I need to put the derivative of lambda I with respect to beta, so I put lambda I over beta. And this summation there is gamma by definition. So really this term is gamma over beta. And if you put all the things together, you get this final formula that you see on the bottom. There is no other, it's just rearranging terms, right? Putting things from one side of the equation or on the other. So you get basically that 1 over beta, that's the optimal beta, is 1 over n minus gamma. And then we have this mean square error that we get, how much error the regression function gives us with respect to the target values here. And as before, we need sort of to start doing iterations because what are the iterations coming here? Is the right-hand side a function of beta? Yes, of course it is, because what is lambda I? I'm sorry, what is gamma? Gamma is this, and lambda I is the eigenvalue of which matrix? Beta theta transpose phi. So there is a beta there. Right? So lambda I and gamma depend on beta. Okay? So effectively, the only way to do this is so obviously these iterations, right? Either you will iterate them simultaneously for alpha and beta or one at a time. But let's say if alpha is fixed, then you assume beta, you compute gamma, you compute a new beta, you come back, you update gamma, hoping for the best. Now, I have to mention that once upon a time, when I first was giving a lecture on this, one of the students told me that he implemented this joint optimization of alpha and beta, and somehow it wasn't converging. Since then, I mention it in every lecture, just in case I inspire one of the students in the class to actually try it and educate me. So we try it once more, okay? Surprises are always good. All right, so that's the evidence. So what are my results? Okay, so if you do all of these things, right, you're going to be able to find the optimal parameters alpha and beta for this model. And so the program that you will see in the slides does this type of calculation, and it even goes one step further. All right. So once you fix the alpha and beta, somebody will say, "But wait a second. If I'm going to use polynomials, let's say, to do this regression, what is the best order of polynomials to use?" I mean, you want to do as few assumptions as possible. So, if it is all about model selection, it's not only to compute alpha and beta, but also to figure out what is the best polynomial that is appropriate for the problem with the data that we have. So for given alpha and beta, what you see here is the marginal likelihood again. And you notice what the order, this is versus the order of polynomial. For polynomial of order 4, okay, I'm starting from 0 here. The the marginal likelihood is maximized, so immediately you can do model selection as well. If you actually try to do this with using, root mean square error for the training and test data, so here, the optimal polynomial is 4, but notice here, for polynomials for the 3, 4, 5, 6, 7, 8, you don't see any difference between the training and the testing error, so it's like not very easy to select the optimal polynomial, but when you use the marginal likelihood, immediately picks and you know what to select. So let me go back to this optimization of alpha and beta and see what all these quantities that we computed actually mean. Okay, do they have any sort of physical meaning, any intuition that can help us? This is the slide that I told you. It's compact, there's a lot of information, so read it, okay? So what I want to do is, I want to put some intuition, basically, why the results look the way they look in these iterations for alpha and beta in this evidence approximation. So what you see on the top is the map estimate, right? This is the exact derivation equation we see the slides from the previous lecture. And so this is the map estimate. And so what I have done is I'm actually rewriting this map estimate in terms of the MLE estimate of W. Okay? You can do this easily. So I multiplied with a few terms here to get the MLE estimate. But effectively what I have is the map estimate versus the MLE estimate. That's very important. So now I don't want to do algebra, but I want you to use your mathematical imagination here, okay? Think that somehow we have an eigenvalue problem for phi transpose theta, right? So this is an eigenvalue problem. So what I want you to think is, instead of using, let's say, x, y, and z coordinates, these are vectors, right? So this is a vector, this is a vector. Think of writing this equation in a basis that consists of the eigenvectors of this matrix beta transpose phi. Right? That's your basis where you're going to write this. So will you agree with me then that the relation between, in every coordinate in that basis, the relation between the map estimate and the MLE estimate will be beta? So I see here beta times phi transpose phi. Would you agree that this will become actually the eigenvalue lambda I of that matrix divided by lambda I plus alpha? Use your imagination. If you express things on this eigenbasis, would you agree that the relation of the component, let's say I of this, with the I component of that will be lambda I divided by lambda I plus alpha? If you have problems, very simple. Beta theta transpose phi, write it down in its eigenvector, eigenvalue decomposition as summation of lambda I ui transpose, plug it in, and then you will see what I'm talking about. But imagining things sometimes helps. Okay? So, what I have here is I plot the mean square error, right? These are my contours basically that give me the MLE estimate. I also have the map estimate that sort of, the prior contours that act as a constraint. So, and we want to basically see the relation of the MLE estimate versus the map estimate. So here, I put, so the data tell me this is the MLE. When you put a prior, it's pushing, let's say, somewhere there. So these contours, right? If you try to write this explicitly, the axis of this ellipsis are 1 over square root of lambda 1 and 1 over square root of lambda 2. Okay? And again, I want to use your geometric imagination because nothing is arbitrary. So the idea here is lambda 1, so lambda 1 here is the smallest of the eigenvalues. Okay? So lambda 1 is the smallest of the eigenvalues. That's why you see here, this is bigger. It's 1 over square root of lambda 1. So for now, you have to trust me that if the lambda 1 is the smallest of the eigenvalues, it implies that the uncertainty in W in the direction U1 is the highest. You can actually see it even here, right? The uncertainty in W1, in U1, is the highest. As a matter of fact, if you go and you look at the uncertainty of W, if you look at the variance of W from the posterior we computed in the direction U1, you will see that's the highest uncertainty. Okay? So I am not making the statements up. So effectively, so lambda 1, the way I have it, is the smallest eigenvalue, right? Corresponds to the direction U1, where the uncertainty is the highest. Now, the uncertainty in W, if it is the highest, that means that data cannot really tell you what, they cannot compute an estimate of W properly. So what does the prior do? What will it do for us? Considering that in this direction, the data tells, I cannot tell you what W is because the uncertainty is too high. So the prior will do what? Look at that picture. What will it do in the direction 1? We'll push the estimate from the MLE estimate to where? To what value of the map estimate? You can actually see the relation here. All right? So this is the coordinates 1 between the W map and the WMLE is going to be lambda 1 over lambda 1 plus alpha. If lambda 1 is very small, what is W map in direction 1? Is 0. So effectively, the formalism, what it does is, it shrinks your estimate for W to 0 because it says, if you cannot evaluate from the data what the correct estimate of W is, I'm going to set it to 0. Okay? This is again the shrinkage effect that we have discussed before, but you can see it here. Okay? If lambda 1 is small, all right, this will become 0. Now, if you take the case of lambda 2, all right, I'm doing this in 2D, so lambda 2 is bigger. So if you have lambda 2 divided by alpha plus lambda 2, then for lambda 2 very big, let's say, or much bigger, the ratio will be equal to 1 approximately. And in that case, the map estimate is closer to the MLE estimate. Right? So effectively, in some direction, you cannot really evaluate an estimate of W because just because of your, the data that you have and the problem that you have, you cannot evaluate what W1 would be. So the analysis, the Bayesian analysis sets that estimate to 0, okay? And that is dictated by the prior. In the other direction, you can evaluate what the estimate is, and so the prior plays no role. So effectively now, if everything has to do, like how many estimates are computed by the data and how many are set to 0, if everything is computed by this ratio of lambda I divided by lambda I plus alpha, what do you think this ratio means physically? The ratio of summation of lambda I divided by lambda I plus alpha. Remember in the problem I have m parameters, right? These are the coefficients. So what does, if some of the parameter, in some of the cases, this thing is 0, in some of the cases not, when I sum all of this together, what do I get? The effective number of parameters. And what does it mean, the effective number of parameters? Is the effective number of parameters that you can compute from your data. Okay, or the other parameters are set to 0. So this number gamma that we see there, it is really the effective number of parameters that they are between 0 and okay? And so actually you can show it, I think it's in one of the slides, if you have a lot of data, basically this becomes equal to m, so there's not an issue. But this analysis can work when you even have less data than n. All right, so you can have less data than the number of parameters, no problem. The prior will set the extra parameters basically to 0. Okay, so so I want you to let me see if I'm going to use this slide. So this is the result that we got. All right, okay, and this is the MLE result. You remember the MLE result when we started talking about regression? This was the MLE result. We said that basically this noise is the sample variance, right? Where this is the regression function, these are the target values. That's basically the sample variance, if you like. But the Bayesian analysis says no, it's not 1 over n, it's 1 over n minus gamma. So is there anything that we have said in the lectures that reminds you of some formula that says the variance equal 1 over n minus something times this mean square error there? In particular, have we seen any formula where it says 1 over beta equal 1 over n minus 1? The bias correction for the variance of the Gaussian. Okay? So effectively, how does the model here corrects the bias of the MLE? It corrects it by basically removing, by accounting for the effective number of parameters that the model can compute. Okay? So this is very, very fundamental sort of Bayesian analysis, right? And it doesn't just come on the simple regression model. You see it literally all over the place. And so obviously here you can do the algebra analytically and you see it nicely, but implicitly more or less this is taking place in many different types of problems. All right, then, so again, you know, the results actually, this is the application of these results in Bishop's example, and there is a MATLAB program that you can play with, and the optimization of alpha and beta, as I said, it happens here separately. I don't know if that's for a reason. Okay, you can tell me. But if you, let's say, keep beta constant and you try to do iterations to maximize the marginal likelihood with respect to alpha, you come up with this estimate, okay? And not surprisingly, it comes out at this point, literally it's very close to the minimum generalization error. So really, if you take a test data set and you try to test the model for different values of alpha, the values that you get here by maximizing the marginal likelihood are about the same as the one after which, you know, the generalization error explodes. Okay, this is just a model that shows you when you play with the effective number of parameters, you can actually see that gamma goes basically from 0 all the way up to m. M is here 10. Okay, so this is the same example, basically, just plotting you something else. Okay. All right. There's a lot of examples that you can consult. So what I want to do now is, we have 15 minutes left. So I want to go back to the regression problems and discuss a few more priors that they are more commonly used than the ones we have seen up to now out of textbooks. Okay. Now, the only thing I'm going to say in the presentation of the slides, I have changed the notation, and instead of defining the design metrics as capital Phi, it is denoted here as capital X. You may ask me why you don't go and change it because if I change it and I do a mistake here and there and I try to compare with the original references, I will completely mess it up, right? It's good sort of to be consistent with the first reference where these calculations have come out from, and so that way I can compare things. And so keep in mind, X is the design metrics, nothing else. All right. So I'm not going to go through the algebra, but I'll take you rapidly through the type of things that you will see in practice, and I think in your homework problem as well. So on the top, what you see is the likelihood, okay? And the only thing that is different, so the likelihood is exactly as before, right? X was our phi before. The only thing that I want to keep here as interesting new aspect is that sigma squared is not known. All right. Before, you remember, we had the sigma squared. It was the precision beta. I call it here explicitly sigma squared. So sigma squared here is unknown. Okay. Before we computed sigma squared with the evidence approximation, right? That's what we did with beta. Now I really want to put proper priors on W and sigma squared. I want to do more sophisticated things than the simple evidence model with fixed sigma squared. All right. This is Gaussian. I'm going to use a conjugate prior for W and sigma squared, and the conjugate prior is a normal inverse gamma distribution. Okay. So I want you, if you have not seen this before, you can look on some of my notes from last semester or last year. So this the joint distribution of W and sigma squared. So it's a Gaussian for W, and notice here is given sigma squared, right? So this is a conditional Gaussian. This matrix here, V0 is given, and then for sigma squared, always you put an inverse gamma distribution with parameters alpha 0 and beta 0. Okay? So this distribution altogether is called a normal inverse gamma, and it is the conjugate prior to a Gaussian likelihood. So remember, I gave you a Wikipedia link. If you go there, you will see basically this, and it will show you what the posterior looks like. So let me take you through the results. So you take this, you multiply with that, you do some algebra, you rearrange things, and not surprising at all, the posterior comes to be what? A normal inverse gamma, right? Because they are conjugate. So if the posterior comes to be a normal inverse gamma, we need to define, before we had the W0, now becomes the Wn, which is given by this nice formula. Before I had the V0 in the prior, now becomes a Vn, is given by this nice formula. And then here I had alpha 0 and beta 0, they become alpha n and beta n. And actually these formulas look wonderful because this is a conjugate prior. You take the prior counts, alpha 0 and beta 0, and you add your data counts. Okay? The derivations are really one slide. But to derive that one slide, maybe I had to write 5 slides of mistakes, all right? But when you put all together and you learn how to close the square on these Gaussians, you get this very nice distribution. Now, if you look at Wikipedia again, or you do the algebra, what you can do is you can actually marginalize this posterior, and you can write the posterior of sigma squared given the data, and that comes to be, not surprising, an inverse gamma. And the posterior of W comes to be a student t distribution. For those who have not seen a student t distribution, it's like taking Gaussians with different precisions or variances and average over them. All right? So obviously, if you're going to compute P of W, you're going to average for all sigma squares coming from an inverse gamma distribution. That will give you a student t distribution. Okay? This has a lot of importance, okay? It's not just another distribution. This is what you will actually see in computer programs when you plot error bars on W. This is, you cannot make much sense of this joint distribution beneath the marginal posteriors given by these formulas. So on this slide, I give you some of the derivations, and also I remind you what the student t distribution is. And you can push the analysis further and say, can you tell us also what the predictive distribution is? And the answer is yes, I can. So if you have a new set of data point, and you notice here I don't use only one data point, little x. I use a whole new design matrix, curly x, right? So if I want to find a solution at many new points, what will be the response? Okay, given my data d. And it comes out, again, not surprising that the distribution is, can you guess, looking at how the intermediate calculations, what type of distribution that will be? What? It will be a student t distribution, and you need to actually do the algebra once in your lives because it involves some interesting steps, including this inversion lemma that comes all over basically machine learning, this Morrison-Woodbury lemma. So when you do this, there is the final result, a wonderful result. Okay, it's a student t distribution. M is the number of points that you want to compute the response. 2an is the degrees of freedom of the student t distribution, and this is the mean, and this is short of the variance. Okay, and I say short of the variance, it's not exactly the variance, but it's short of the variance of the student t distribution. Okay, Vn and Wn, remember, they were coming from the posterior of W that we compute in the early slides. Okay. So it's not really difficult to do this full analysis, right, with sigma square unknown and put the proper priors. So this is a much more sophisticated than the evidence approximation we use. But in practice, people will do even more simplistic things. So they will use this very general prior and sort of push it to different uninformative limits. So I want to show you these uninformative limits because when you read papers, this is what people most probably will use. Okay? So, here is one case. You are going to use an uninformative prior for sigma square. So you're going to set alpha 0 and beta 0 equal to 0. Okay? And you're going to take for your Gaussian W0 to be equal to 0. And you're going to set this matrix V0 to G, some constant, X transpose X inverse. I remind you, X is your design matrix, is our phi that we were using in the previous analysis. So the V0 is going to be some constant times X transpose X inverse. And this is called Zellner's G prior. If you have never seen it before, it's weird. It violates all the laws we have seen about prior models, and it's weird because a prior should not depend on the data, but this prior depends on X, right? So it seems, there is an issue there, but on the other hand, it has lots of nice features. It works. It's invariant to the scaling of X, and it is used very often in regression analysis. Okay, so this is what is called Zellner's G prior, and this is basically a summary of it, if you like. The distribution of W given sigma squared is a Gaussian mean 0, and the variance looks like this, and the inverse gamma is an informative 0,0 coefficients. All right. So there is a physical meaning. You can interpret G as a certain number of real measurements, all right? The way we have seen this with conjugate priors. So I'm going to bypass this. I'm going to give you two more uninformative limits. So this is one of them. Very weird. You're not going to see it very often. So effectively, you're going to, since it's uninformative, you're going to take the variance in W to be infinite. You say, the mean is 0, but I have no idea what the value of W is, so take that thing there equal to infinity, okay? And you keep the inverse gamma uninformative to 0 to 0. So this actually goes to sigma to minus d plus 2, where d is the number of parameters that we have. Okay? The d plus 2 comes basically from the normalizing factor of this Gaussian. Okay? So this is sigma to minus d plus 2. We have never seen any, remember we spent the lecture talking about prior models? I don't think we have ever seen anything like that before. Okay, that's very weird. You know what we have seen? Have we seen this? Yes, we have seen this. How do you get this? If you assume W and sigma squared to be independent, make this a uniform, 1, and take this Jeffreys prior, which is 1 over sigma squared. That's the result. And you can actually get this result by the following choices. All right? So here, instead of choosing 0, you have to put this weird number minus d over 2. So if you put minus d over 2, you get this sigma to minus 2. All right. So for if we use this prior, okay. So let me go fast because we have only 4 minutes left. So if we use this uninformative prior, okay. So it's a limit basically on this conjugate prior we discussed, and so if you use that and you compute the margin, you compute the posterior of W and sigma square using the derivations that you saw before, and then you compute the marginal posterior of W, you get this wonderful formula that the marginal posterior of W, it is a student t distribution centered around the MLE estimate of W, very easy to compute, and it has a variance like that is S squared divided by n minus d. N is the number of data, d is how many parameters you have, and S squared is the error that you do from the target values when you use the MLE estimate as W. All right, so S squared is something you can compute using these squares basically, okay? S squared is given like that. So why is this result extremely important? Because this result, by sort of a mistake of nature, comes to be identical to the result that people in the frequentists get by using the sampling distribution of the MLE. And I'm not going to elaborate much, but if you check standard statistics books, it comes out that the error bars in W coincide with the error bars basically frequentists get and plot in books and papers, okay? But this is a fully Bayesian analysis, all right? So if you do a calculation, let's say, and you want to plot error bars on W, basically what you need to do is take the diagonal element of this, plus minus, 1 standard deviation. That will give you the error bars on W, and it's extremely simple to compute. S squared, trivial, and you need the metric C, and the metric C for this uninformative case, it's really nothing else but X transpose X inverse. Okay, so everything is in place. So, so this is how this looks like for one coefficient. Okay, it's a student t distribution. For those who again are not comfortable with the student t distribution, if you have lots of data, it converts to Gaussian, but it has fat tails. Okay, so it's not exactly Gaussian, but it looks like a Gaussian. So one of the common problems that I gave, which I think is most probably the best common problem you can do in regression models, was the so-called caterpillar example, where we had fitting a data in how many dimensions? Anybody remembers? 11. So it was fitting data basically. This was 11-dimensional problem. So imagine, you do this simple thing, right? The program is maybe, 30 lines or so, and you compute the coefficient, the map estimates. This is the map, the mean basically of W, because it's a Gaussian, let's say, it's a student t distribution. And these are the 95% confidence intervals. And these intervals are extremely important because, you know what? If you look at some of these intervals that I mark here with stars, they don't contain the value of 0. And you know what that means? The coefficients that are marked with star are important. The other ones that cross the value of 0, right? In average, basically they're 0, okay? And it comes out, indeed, if you completely remove in your regression analysis all the coefficients and the basis functions for those things that don't have a star, that selection of parameters basically you will do is the right selection of parameters. And in the Homer problem that we had last semester, we actually gave different ways of verifying this, including sort of doing sampling over different regression models. All right, I think the light will go off, and so I am going to abandon you there. Remember, there's no class on Tuesday. I'm going to see you back on Thursday.